170. Oh, thank you. The prediction was that at a certain time, sometime around 2:44 Universal Time, which was about 9:44 p.m., that this particular star right here was going to be blocked because the asteroid 173 Eno was going to pass right in front of it for up to possibly 9 seconds. So that's a pretty big asteroid. Well, it's a big asteroid. You can tell because it has the number 173. So it must have been pretty big to have been discovered hundreds of years ago. Well, 100 years ago anyway. So I went out and I got my telescope and I pointed at this place. It was a little bit stressful because I couldn't set up the telescope well in advance because a certain person was using the telescope for her course with her students. And I had to wait for them to finish, but eventually she did finish. And then I pointed the telescope, and what I'm going to do, I'm going to show you a series of the pictures I took. So I cut the image down in size so I could take pictures pretty rapidly with my camera. And I told it to just snap pictures as quickly as it could, roughly 1 second exposures with about a 0.6 second dead time in between to read out. And I put a little time tag here, and you can watch and tell me if you see any change in the brightness of that star to which my cursor is pointing. And if so, how long did that last? Let's watch again. You guys count how many frames. 5 or 6, 4 or 5, depending. There was one. If I went and made measurements, and if you look at the light curve of it, there was one partially covered, 1, 2, 3, 4 fully covered, and then one coming back out. So anyone who's interested in doing this sort of measurement, it's a thing that amateur astronomers do more than professionals, because even though there are lots of occasions when these little asteroid shadows pass over the Earth, they're not always, they only cover a very small portion of the Earth. Most big telescopes are sort of fixed in place, and it's only rarely that an asteroid passes in front of, say, Kitt Peak. But if you have hundreds of amateurs around the country, there's a pretty good chance that one of those shadows is going to go over somebody's backyard. And so people who are willing to go out and take their chances, maybe one time in 3, it actually happens, and the other 2 times, the position of the star is a little bit wrong, or the position of the asteroid due to its orbit not being known is a little bit wrong. If you're willing to put up with those chances, you can make these measurements and then report them to people. And there are a group of people who take these measurements and they refine the orbits of the asteroids and the positions of the stars. You can even measure the sizes and sometimes the shapes of the asteroids by making a series of measurements. I see a hand. That time, as I said, was about 9:42 or 9:43 in the evening of February. Yeah. Yep. There you go. And if you're interested, contact me, and I can tell you where you can go to look for predictions, big websites full of here's all the things that will happen in the U.S. in the next month or the next couple of months. And there's some nice software that's free and easy to download that will run on your computer and make the predictions for any place you choose. So good stuff there. But that's not what I'm here to talk about today. What I'm supposed to talk about today is an introduction to Stromgren spheres. And so I'm going to try to tell you what they are and why they're named Stromgren spheres and how they work, the physics behind them. And if you followed my advice, and brought one of these with you, I hope I have a place at the end where you can do some calculations and you can calculate the size of a Stromgren sphere around the sun, hint, not very big, and around a big O star. And you can see if your calculations agree with those of, spoiler alert, Mr. Stromgren. Also, as Tony mentioned earlier, we have 2 door prizes that were donated by Nick Lamandola. So we have and I noticed this really works because I can look at the projector and I can actually see the lamp of the projector. It's much more comfortable through this than it is with the naked eye. So I will give these away to people who can provide correct answers with their calculators this evening. So fire them up. Okay, so what is, let me get this out of the way, if I can get this out of the way. I'll put it up here. So I'm going to start off by showing you some pictures of Stromgren spheres. You've seen them before, even if you didn't know it. So this is an object. I think some of you know its name. Does anyone recognize this object? Say it. It's the Rosette Nebula. It's the Rosette Nebula. So this is a big cloud of gas in space, which is glowing, clearly. And it's glowing because there's a cluster of several very hot, very large, very luminous stars. They emit a lot of light, as we will discuss. It has to be a particular type of light. And that light runs into the gas that surrounds the stars, ionizes it, and excites it. And when the gas turns back to neutral, it emits light. And that's why we see these glowing. So this is the Rosette Nebula. It's one example of a Stromgren sphere. Here's another one. This is a new one to me. I wasn't familiar with the Spirograph Nebula. Have you seen this one before? I think this is a really small, faint one. It looks great in this HST picture, but if you don't have HST, it doesn't look so good. And also, if you have the Hubble Space Telescope, you can look at the Orion Nebula. These are really up close and personal pictures of little tiny portions of various places in the Orion Nebula where there are protostars just forming right now. They haven't really fully turned into stars yet, so there's lots of gas surrounding them. Some of it is still collapsing. There's probably disks around some of them. But they also produce, as you can see, little glowing clouds of the gas that surrounds them. That's another example of a sort of a Stromgren sphere. These are sort of Stromgren teardrops, I guess. So you've seen lots of pictures of glowing gas clouds in space. Have you ever wondered why do they do that? And I guess, how big do they get? Well, that's what I'm going to try to explain today. And I welcome audience members to ask questions in the middle. You don't have to hold your question down. Just raise your hand or shout it out, and I'll see if I can answer it. Same goes for those of you at home. You probably should shout it out, because I won't see you if you raise your hand. All right, so the main features of a Stromgren sphere are that you have a hot star, and the fact that it is hot is very important, as I will explain later. That there's a cloud of gas around that hot star. And you may have seen in some of those cases, not at all, sometimes there appears to be a pretty sharp boundary between the glowing lit up part of the gas and the sort of general boring space part beyond it. So I'm going to sort of try to tell you what's going on. And the first thing I'm going to try to do is explain why they're called Stromgren spheres. And the reason they're called Stromgren spheres is because they were first explained in depth by a guy named Stromgren. Not too surprising. He was a Danish astronomer born around the turn of the 20th century in Denmark. And it's no surprise that he became an astronomer, because this, believe it or not, is the house in which he grew up. His father was the director of the Osterwald Observatory in Copenhagen. So there's a telescope at the center. They lived at one end of the house, and there was another telescope at the other end of the house. So you grow up in an environment like that, it's pretty hard not to become an astronomer, I would say. Does anyone know who this guy is? The picture. He does have a brass. Yes, he has a fake nose. That is a picture of Tycho Brahe, the wonderful Danish astronomer who had his own island observatory and was the best pre-telescopic observer. He was number one when it came to measuring the positions of stars and planets in the sky. So Stromgren was, as I said, born around the turn of the century. He followed his father working at that observatory. He published his first paper at the age of 14, so he got an early start. His father tutored him in mathematics and science because he couldn't wait. And it was in 1939, that he published a very influential paper, and that was the paper that discussed what happens when a hot star emits photons into surrounding gas. And it was that paper that caused people to say, hey, we ought to name these glowing clouds of gas Stromgren spheres, because he's the one who first put a mathematical basis into explaining how big they should be and how much bright light they should give off and all that kind of stuff. What I'm going to do tonight is take his paper, which was 22 pages long and had a lot of math and went into a lot of detail about the complications. I'm going to ignore all those complications, and I'm going to give you the simple version where we assume everything is as simple and easy as possible. He did not do that. He did the real thing, adding in things like, oh, what if it's not pure hydrogen? What if there's helium? How does that affect things? I am not going to discuss that. But if you want to know, you can click on this link. Just click on the link, and it will take you to a place where you can get a copy of the paper, and you can say, hey, show me that paper by Mr. Stromgren, and there you go. You can start reading it for yourself. So if you want to, you can read his paper. All right. He wasn't just a theoretical astronomer. It turned out he was a very good observer, and he came up with a way of choosing filters, special filters, not the usual RGB ones that you use today for photography or the UBVRI ones that astronomers use. He came up with a series of filters that had particularly chosen pass bands. They were sort of narrower than the standard filters, but he put those narrow bands in just the right places in the spectrum that they isolated certain features of stellar spectra and made it very easy to distinguish, say, a B star from a G star, from a K star, from an M star, without having to take a spectrum. And so his series of passbands and measurements has been known as Stromgren photometry and Stromgren filters. And so he wasn't just a theorist up in an ivory tower. He was also an observer. So he could do it all. He was invited to become director of the Yerkes Observatory, and he is at the center of the front row of this picture. This was taken in 1937, I think, and here he is. Does anyone recognize any other astronomers or people that might be in this photograph? Right here, front row, second from left, is in fact Chandrasekhar. That is Chandrasekhar of the Chandrasekhar limit. Yep. And there's a couple of other people. That guy in the back is identified. There, you can click on this link and it will tell you who the people are. This guy's identified as tall. Tall. Yes, tall. I think Otto Struve is lurking in the background. I think one of these guys, that one, is probably Otto Struve. You've heard of Struve. Anyway, so Stromgren was a really good astronomer, and he was recognized for his excellence, director of the Yerkes Observatory. And then, in 1957, he left Yerkes to take a position at the Institute for Advanced Study, where they said, oh yeah, you can take this office. It used to be used by this guy named Einstein, but he died, so you can use it instead. Yeah. And he stayed at Princeton for 10 years and then went back to Denmark. He died in 1987. He published his last paper just a few months before he died, so he continued to do research his entire life. So, way to go, Mr. Stromgren. Okay, so that's sort of the biographical part. Let's talk about the scientific part. So to understand why stars create these glowing clouds, we have to figure out what happens when light meets an atom. So let's look at that. So here's what happens. When you have a neutral hydrogen atom, it consists of a nucleus made up of a positive proton, and around it circles an electron, which is negative. If a photon comes and runs into that atom, if it is energetic enough, if it has enough energy, it can knock the electron and the proton apart so that they split up and do not come back together, and they fly off separately into space in other directions. And we call that process ionization. It turns neutral hydrogen, which astronomers call H1, into ionized hydrogen, which astronomers call H, 2. Now, it's really, you have to be careful because ionized hydrogen, where the proton and electron are separate, is called H Roman numeral 2. If you have a neutral hydrogen atom and it meets a neutral hydrogen atom and they fall in love, those two atoms create a hydrogen molecule. And because there are two hydrogen atoms in a molecule, you know what they call that? H subscript 2, H subscript Roman numeral 2. So H2 can either be the ionized version or the molecular version, which is very annoying. But I'm only going to talk about neutral or ionized. So sometimes the Stromgren spheres are called H2 regions because they're full of this ionized gas. The crucial thing is that the photon in this process can't be an ordinary optical photon, like the ones hitting our eyes right now, the ones coming from the lights overhead or from the projector. Those photons cannot break a hydrogen apart. Only ultraviolet photons of a certain type, which we will talk about, have enough energy to do the job. So this is the process of ionizing hydrogen. What happens if you ionize some hydrogen so that there's lots of electrons running around on their own, and there's protons running around on their own? What happens if you leave all those charged particles around for a while? Well, the negative electrons and the positive protons feel an attraction, and so sometimes they'll meet and combine to form hydrogen again, to form a neutral atom. It turns out that when a proton and an electron meet and form an atom, they get rid of a bunch of their energy by emitting photons. And it's the photons that are emitted when these ionized hydrogen atoms recombine. That's the very distinctive red that you see when you look at a lot of nebulae in space. The red color you see in the Orion Nebula or the Ring Nebula or a lot of other nebulae, that red color, as we will see, comes from a part of this recombination process. Okay, that was the simplified version. I have to get into some equations and math. So those of you with your calculators, this is the time to get them out. Yes, I know you're looking forward to this, small son. She's one of my students. She's a math nerd. It's excellent. Yes. All right, so let's look at this in more detail. If you look at a neutral hydrogen atom, it turns out that the electron can't go wherever it wants. It can't wander willy-nilly different. It has to sort of stay in a set of particular orbits. It can be in this n=1 lowest orbit closest to the nucleus, or it can be a little farther away if it orbits at this distance, and we call that the n=2 level, and then there's an n=3, which is a larger orbit, n=4, which is bigger, and then there's n=5, 6, 7, all the way up to very large numbers. The electron can't be anywhere in between. It can be here in n=3, or it can be here in n=2. It can make sharp jumps and jump up or jump down, but it can't go halfway. That's one of the weird things about the way atoms work, is that the energy levels are quantized. And in hydrogen, they're particularly simple and easy to describe because there's just one electron and one proton. So these different orbits have different energies. The lowest energy state, when the atom has very little energy, the electron is down close to the nucleus. If the atom gains some energy by maybe colliding with something or absorbing some light, the electron might jump up to go to the 2 or 3 or 4 levels. And it turns out that each of those levels has a very particular energy. The amount of energy in energy level n, like n=1 or n=2 or n=3, is given by this formula. We use a convention where if the electron is running free far away, it has 0 energy, and then it kind of loses energy if it falls into the atom, and you have to then give it more energy to get it back out. So all these numbers are negative here. But the important thing is that there's more energy at high levels, and there's less energy at low levels. So I've used this formula And I've just written on this little diagram how much energy a few of those lowest levels have. So the ground state, negative 13.6 electron volts. What's an electron volt? Who cares? And then 3.4 electron volts. It's a unit of energy. It's very small. It's convenient. Okay. So if an atom is in one energy state and the electron decides to jump down to a lower state, like here, the atom is jumping down from the n equals 3 to the n equals 2 state. What happens is the electron loses energy equal to the difference between this number and this number. So if you calculate the difference, those of you with calculators, calculate the difference between those two energy levels, it tells you how much energy this photon will carry away. So the atom releases a photon, the photon flies off into space. Maybe if you're lucky, you see it with your telescope. So those of you with calculators, can you tell me how much energy that electron must have? I see, oh, what? Go ahead. 1.89 electron volts. Did anyone else get 1.89 electron volts? Very good. Good, you don't win anything, but that's good. You are going to win something if you can answer the next question. So the next question is, suppose that a hydrogen atom jumps from n equals 3 down to n equals 2, and it loses 1.8, what was it, 1.89? 1.89 electron volts, and a photon is created with an energy of 1.89 electron volts and flies up into space. I wonder what color that photon would appear. Is there some, I'm ignoring you, is there some way that we could calculate the color of the photon? Would it be blue? Would it be orange? Would it be green? Well, it turns out the energy of a photon is related to its energy. Sorry, energy is related to the color. But there's another thing that maybe you're more familiar with. You guys know about wavelengths? Wavelengths? If we knew the wavelength of the photon, we know, like in the visible optical spectrum, the blue end is around 4,000 angstroms and the red end is around 7,000 or 8,000 angstroms, and yellow's in between. So if we knew the wavelength, we could figure out if it was red or yellow, blue, green, indigo, or violet. Well, fortunately, there's another equation, very handily, that converts between electron volts of energy and wavelength. All you have to do is take this curious constant of 12,400 and divide by the amount of energy in EVs. So if you have the amount of energy in EVs, and you use that on the bottom of this equation, you could calculate the wavelength of a photon given off by a hydrogen atom as it jumps from n equals 3 to n equals 2. And if you were the first person to yell it out loud correctly, you'd win a prize. I heard it over here first. Sorry, I heard it over here. What? Choice. You could get this wonderful thing that covers your face, which in your case, or you could get this. Which one? Vinyl. You want the vinyl one. Congratulations. Well done. You brought your calculator. You should bring your calculator with you everywhere, wherever you go. You never know when a pop quiz could just suddenly take over. So it turns out it's about 6,563 angstroms, or 656 nanometers, and that is deep, 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 deep red. That's the red you see. It's hydrogen atoms jumping down from n equals 3 to n equals 2. It's called the Balmer alpha emission line. Hydrogen alpha, Balmer alpha, yeah. So when you see that color in space, you know that there's a lot of hydrogen and it's been excited, and atoms have combined after being ionized, and as they jump down from n equals 3 to n equals 2, boom, they release these deep red colors. All right. So, in order for that to happen, you first have to break the atom apart so that the electron and the proton go their separate ways. When they recombine, that's when they're going to give off those photons. So in order to get the glowing gas, you have to ionize the hydrogen. So how can you ionize a hydrogen? So I have a sophisticated diagram here. I have a sophisticated animation. Those of you not accustomed to strobes or something, may have to watch it. I'm going to try to show you what the process of ionization looks like in detail. Yes, the photon comes in, it knocks free the electron runs out. What you're doing is giving the electron enough energy that it can not only go from n equals 1 to n equals 2, but to n equals 3 or 4, but over to n equals infinity. You're giving it enough energy to escape the atom entirely. And that is a lot of energy. It turns out you have to jump all the way from n equals 1 to n equals infinity, and the energy difference in that case is, what did you say? Wow, you did that without getting a calculator. That's a lot of energy. The photons that you see right now with your eye, they don't have that much energy. The photons your eye sees have at most maybe 3.5, maybe 4 electron volts. So something with this much more energy, 13.6 electron volts, it would have to fall in a different part of the spectrum. What part of the spectrum would that be that has more energy than the optical? Exactly. I wonder what wave you need. That's great. Too bad I'm not giving you a prize for it. But you could use it. It turns out that the answer is something like 912 or 911. And that is the critical, get bigger you. Hello. Why is that not? Go back there. Oh, I see. Good. Okay. 912, there we go. 912 or 911. There you go. That photon, that critical wavelength is just enough to ionize a hydrogen. And if you have more energy, which means a shorter wavelength, then you can definitely ionize a hydrogen. This is sometimes called the Lyman limit, after Theodore Lyman, who was a physicist in the US who studied these transitions in the ultraviolet made by hydrogen. So it takes an ultraviolet photon whose wavelength is less than or equal to 912 angstroms to ionize the hydrogen, and therefore to produce the pretty glow, and therefore to make a Stromgren sphere. So how do we make high energy photons? Does the sun, our very own sun, does it make high energy ultraviolet photons? I see a well-known scientist who is shaking her head. No, it doesn't. Well, I mostly agree, but there's a little tiny part of me that says, maybe. The sun is a pretty typical main sequence star. Main sequence stars are big glowing balls of hot gas. And to a fair extent, not exactly, but to an approximation, they emit light in a particular way that is a simple kind of way that we call a black body spectrum. And the shape of their light, if you were to measure how much light they give off, that's on the vertical axis here. So lots of light at the top, not much at the bottom, versus wavelength. It has a particular shape. There's a peak where it gives off a lot of energy, and then there's, at longer wavelengths, the amount falls off gradually. But at shorter wavelengths, towards higher energies, it falls off a cliff. This is the spectrum of the sun in blackbody form, so it's a simplified version. And you can see that I've placed a little line here at a wavelength of 912 angstroms. All the photons that are on the right-hand side of the line at longer wavelengths, they cannot ionize hydrogen. Only the photons shown over here on the left can ionize. Now, if you look at that, you might say, oh, it's okay, the sun is still emitting some photons at those short wavelengths. But if you look at the scale, you might notice it's not a linear scale, it's a logarithmic scale. So at the peak here, which is sort of in the visible spectrum, our eyes can see, the sun is emitting something like 10 to the 13th units, whatever those are, I won't bother to explain. How many units is it emitting down here at 912 angstroms? Let me go across here. What does that say? That says 10 to the 5th. This was 10 to the 13th. That's 10 to the 5th. That's a factor of 10 to the 8th. That's 100 million times. The sun emits 100 million times more energy here than it does there. Basically, the sun emits a little tiny bit of ultraviolet ionizing photons. So it can ionize some hydrogen gas, but not much. It's just not hot. It turns out that the wavelengths emitted by a black body depend on the black body's temperature. The hotter it gets, the shorter the wavelength. The spectrum sort of shifts. It kind of looks like this. Here I'm showing you the sun in red, but then a hotter star in green and a really hot star in blue. And you can see that not only does a hot star emit more light from every square meter of its surface, because these are all higher, but they also shift towards shorter wavelengths. And in fact, this star with a temperature of 50,000, the one shown in blue, the peak of its spectrum is shorter than 912 angstroms. So it is emitting a boatload of high energy ionizing photons. If you want to ionize hydrogen, you should get yourself a really hot star. So now we're going to get back to the calculator stuff. If we wanted to know quantitatively, like just how many ultraviolet photons does a particular star emit, because we wanted to figure out how much gas it could ionize, we could figure out how brightly it would glow in red light, well, we'd have to calculate these numbers of how many photons. So I did that using math. And there's equations that tell you how much energy is emitted at different wavelengths by a black body of a certain temperature. Yeah, so I did math. And I won't bother to explain all the math, but what I'll tell you is the answer. Here's a simple comparison in number form, in tabular form, of how many photons are emitted from every square meter of the photosphere of these three stars. One of them is like the sun. The first one here is a sun-like star. And then the middle one is a pretty hot star. And then the bottom one is a really hot star. There aren't many stars hotter than this. This is like the most massive 20 solar mass star, which are very uncommon. They produce a lot of ionizing photons. Look at the ratio here. More than like 10 to the 11th times as many. So here is a graph showing on the vertical scale how many ionizing photons each star produces as a function of its temperature. And yes, when you get hotter, you produce a lot more ionizing photons. So if I wanted to do a calculation, how many atoms could I ionize? I have some of the information I need right here, based solely on the temperature of the star. But that is not all that matters. In addition to stars like the sun being cooler than B or O stars, there's another difference. The O stars are more massive. They're hotter. Is there anything else that makes an O star different than a solar type star? That's true. Not the answer I'm looking for, but you're absolutely right. Any other physical characteristic of an O star that might distinguish it from a G star like our sun? Oh, in the back, root sun. Are you telling me that O stars are bigger physically? You're right, sir. Let's look. Why? Did you happen to scroll down to the next page? I'll bet. What? No, you just knew that because you're a good student. So here you can see a nice graphic that some NASA people made that sort of compares. If you could put stars of different spectral types side by side. The sun is a G star like this one, temperature about 5,800 Kelvin. The B star that I've been using, temperature about 15,000. Here it is. It is certainly bigger than the sun. And an O star, that really hot one, temperature about 50,000, is bigger still. This is roughly 4 times the radius of the sun, and this guy is like 16 times the radius of the sun. That means that even though they're hotter, so each square meter is producing more ultraviolet photons than the sun, they're also bigger, so they have more square meters. So you have to combine the extra area on top of the larger number of photons per square meter if you want to calculate how many ionizing photons these hot, big stars produce. So I did that. And I just factored in the extra surface area. And now, over here in this rightmost column, you can compare the total number of ionizing photons that each star produces. And you can see the sun produces what seems to be a lot, but when you compare it to the number produced by some really hot stars, it is puny. And here's that same information in graphical form. So an O star produces something like 6 trillion times as many ionizing photons as the sun. So we can expect hot O stars to produce way more impressive ionized regions of glowing gas around them. Okie dokie. So finally, the end product of all these calculations is how big is the sphere supposed to be? So here is their sort of schematic. We have a star shown here in blue, a hot blue star emitting ionizing photons. Those photons goes off. They run into some hydrogen gas that surrounds them, and they ionize that gas. And so they produce ionized hydrogen, H2. But then eventually that hydrogen gas absorbs all of the ionizing photons, and so there's a region beyond which the gas is just normal neutral hydrogen minding its own business, not glowing. So we expect, if the interstellar medium were perfectly simple, where it was all hydrogen with no helium or oxygen or anything else, and there were no motions in the gas and there were no winds, they were just static, we'd expect to see a beautiful sphere of a certain size surrounding each hot star. In real life, they all get crinkled and turned and crumpled and made funny shapes. But in this ideal world, we'd expect a nice, perfect sphere. And the goal for the next 5 minutes, which could win you this, the goal is to figure out how big, what is the radius of this ionized region, this Stromgren sphere that surrounds a particular star. If I tell you how many ionizing photons the star produces, can you tell me how big is this glowing area around it? That's the big question. So, it turns out that this calculation is exactly the one that Mr. Stromgren did in his paper published in 1939. And you could go and look at it, and we will look at one feature of it in a moment. He made a proper calculation that doesn't involve all the simplifications I've been using. So his version is much better than mine. But what I'm going to do is assume it's pure hydrogen. There's no nearby other stars. There's no strong stellar wind. There's no motions in the gas. And I'm going to assume that we have reached the steady state. What does that mean? It means that the star isn't increasing the number of ionizing photons, so the sphere is not growing, nor is the sphere shrinking. The star is producing ionizing photons at some rate, and the gas is absorbing at some rate, and they're just exactly canceled. So there's a perfect balance. A balance between the ultraviolet photons from the star ionizing atoms and the separated electrons and protons recombining back into atoms. If we can get the radius that gives us those two processes exactly the same, then we'll find that radius of the Stromgren sphere. If the sphere is too small, some of the photons get out. If the sphere is too big, some of the photons don't reach the edge. We need to find the radius that is just right to bring these two processes, ionization, recombination, into balance. We need to find just the right radius. And if anyone can name the cartoon from which this still was taken, I will give you $1. Bugs Bunny and the Three Bears. This is a Bugs Bunny cartoon. It's a classic. It is a classic. I could quote you. The voice of little baby bear is awesome. He's little baby bear. His father. Anyway, enough of that. So, Mr. Stromgren was the first one to put those words. I want to find a balance between the ionization rate and the recombination rate. So here's what he did. He said, I'm going to make an equation. I'm going to put the rate at which the ionizing photons come out of the star on the left-hand side. And I'm going to put the rate at which protons and electrons recombine on the right-hand side. And I'm going to set them equal and see what happens. So the number of ionizing photons, that depends on the temperature of the star and the radius of the star. I made a table. We can just grab the number from the table. Now, this part, how many recombinations take place, depends on two factors. One of them is how much stuff do you have? How big is your sphere? So that's this factor here on the right-hand side of the right-hand side. And the volume of a sphere is just 4/3 pi r cubed, right? Well, the tricky bit is this one right here. In every little cubic centimeter of that sphere, there's a bunch of electrons and there's a bunch of protons. And the more of them you have, the more recombinations you'll get. So this, I don't know what that was. I'm going to pretend it didn't happen. The rate at which the protons and electrons meet obviously depends on how many electrons I have and how many protons I have. Okay, good. And there's one more factor, which is this letter alpha. That stands for some physical constant that relates how quickly the protons and electrons, how efficiently they can meet and join up. And if you know the value of the alpha and you know the density of the gas around the star, then you can figure out everything in this equation. You can rearrange it to put the radius over on the left-hand side and everything else on the right-hand side. And that gives you an equation that tells you the radius, theoretically, of a Stromgren sphere, the radius of the glowing cloud of gas that will surround a star. The things you need to know are how many ionizing photons it produces, up on top there. You need to know the value of this physical constant, which you can measure in a laboratory. And you need to know how dense is the gas around it. And the density of the interstellar medium changes from place to place, but we can just adopt a rough round number to see what happens. So, those of you with calculators, what I'd like you to do, we're going to compare two stars. So I get this formula here, and I have the value of the alpha. That alpha constant is 3.1 times 10 to the minus 13. And I have the value of the hydrogen density. Let's pretend that the interstellar medium has just one, count them, one atom in a little box, 1 centimeter on a side. So your hand, if you make a fist, is probably 5 or 6 cubic centimeters. You'd have your hand would be full of 5 or 10 atoms. So if you were to use those values and you were to pick a really hot, big, massive O star that emitted almost 10 to the 50th, 9 times 10 to the 49th ionizing atoms per second. You could use this formula, and you could calculate the radius of the glowing cloud of ionized gas that should surround it. On the other hand, if you wanted to make the sun feel inadequate, you could plug in the number for the number of ionizing photons produced by the sun, and you could calculate the sphere of the ionized region that should surround the sun and does surround the sun. If you go into interstellar space with sending a spacecraft to Jupiter, it flies through an ionized solar system. The gas in between is mostly separate electrons and protons. So anyone with a calculator out there, I'm going to give everyone a minute or so, and then I will use some scientific process to choose one of the guessers scientifically, and if that guesser has the right value, I will give away this wonderful solar filter. Let's see, we got people with, no, this person with the calculator either has already done it or he's quit. I got some other people with calculators, they're working on it. I got people back there, people there. Okay, I got one person with an answer. Anyone else who thinks he has an answer to the O star? How big should the Stromgren radius be? I got another person with an answer. We got young person compared to me. Young people. All right, we got another person. All right. I got one there, one there, one there. I'm going to use a scientific method to choose one, and we'll see it. Eeny, meeny, miny, mo, catch a tiger by his toe. If he hollers, let him go. Out goes Y-O-U, and you shall not be it. You're out. Eeny, meeny, miny, mo, catch a tiger by his toe. Yeah. You're it. You're it. What is your value? 4.2 times 10 to the 20th centimeters. Wow. Well, is that correct? Now, now, how big is that? How big is 4 times 10 to the 20th centimeters? Is that we usually don't use centimeters when talking about distances between stars in space, right? What units would you feel more comfortable with? Meters? Okay, it's 4 times 10 to the 18th. But that still is kind of weird. Anyone else? Are there other units you use? What units do you use talking about distances between stars? Light years. You do. That's an excellent unit. What if you were an astronomer and you wanted to talk about distance between stars? Parsecs. Let's do parsecs. If you take your number and divide by 3 times 10 to the 18th, that's the number of centimeters in a parsec. So if you took your 4.2 times 10 to the 20th and divided by 3 times 10 to the 18th, what would you get? 136 parsecs. Let's see what Mr. Stromgren thought. Oh, look, it's Mr. Stromgren's Table 5 from 1939. Let's see, you'll pick an O5 star, 140 parsecs. Well done. That's good. So there you go. You have won this wonderful. So if even this very, very simple model can give you reasonable answers, real Stromgren spheres are going to be different than this for a number of complicated reasons, but they'll be within a factor of 2 or 3. So that's pretty big, 140 parsecs. That's like distance from the sun to pretty distant stars. Like the nearest star is only about 1 parsec away. We'd have lots of stars in a region that big. You might, in fact, see a Stromgren sphere. You might expect to see some of these that enclose many stars, reaching out tens of parsecs and therefore enclosing lots and lots of stars, which some of them do. Now, it depends very critically on the density of the gas. If the gas is really dense in some region of space, then this Stromgren sphere will be small because there's more atoms to absorb those ionizing photons. They can't go as far. So the numbers here are just guidelines. You can use the equations we came up with. If you have a different density of gas, you can just put that density right there and then recalculate, and you'll get a different answer. Yes, sir, in the back. So the donut hole is not supposed to be there. The reason there's a donut hole there is those stars are not just emitting ionizing photons. They're also producing winds of particles that fly off their surfaces and they push the hydrogen away, hollowing out a space like a donut hole. Stromgren didn't deal with that. He wanted to do the simple stuff first. So if you're trying to figure out how big is the donut hole and what does that do to the size of the sphere, that's more complex. And I certainly don't know the answer. You'd have to know a lot about properties of the stellar wind. That is a good question, though. As in real life, they're almost always way more complicated than this very simple calculation. So that, I hope, has told you something about blowing clouds of gas. There's some links you can use to read other materials if you want to pursue this further. And I'll be happy to take any questions you have now. Yes. Yes. So that is an excellent question to which I don't know the answer. If I were to read his paper more carefully, if anyone were to read his paper more carefully, I'm guessing he would tell us the source of his value. And I'm guessing, pure guessing, that he was using a value that was calculated. Theoretically, I don't know. It's a good question. But I know that it can be measured in addition to can be calculated, so you can get a check on things. And it's probably way more complicated than, it probably depends on other factors, blah, blah, blah. But yes, question. Yes. So the question was, if you understood the properties of the winds coming off of a star, then you could calculate what its impact should be on the surrounding gas and how much it should push the gas away and how large a gap it should produce between the star and the glowing gas. And I think that all of that is true, and I know that there are lots of papers who study the question of what's the impact of stellar winds on the surrounding material. And I am not the sort of astronomer who studies that, so I know nothing more than I've just told you. But I know there are people who do, and there's lots of papers. Other questions people won't ask? Yes. Mm-hmm. Right. Yes. Yes. So way deep in the interior of this O star, the temperatures are probably 3 to 10 billion degrees Kelvin, which is really hot. The thing is, even though way deep inside, there are hugely high temperatures producing really, really energetic photons, gamma rays, X-rays. Those can't get out into space and interact with the hydrogen because they have to fight their way through all this other gas. And as they fight their way through all this other gas, their very high energies get shared with the atoms around them. And by the time they reach the photosphere and can escape into space, their energies have decreased till they're only ultraviolet or optical. Yeah. So there's some really funky stuff that happens when some stars turn into planetary nebulae. They blow their outer layers off gently, and they leave the core of the star exposed. And for a brief time, it's as hot as it was. And so there's a brief period when objects like this one up here, this one here, that one, that is the core of a star, which is really, really hot, maybe 30 or 40,000 Kelvin, that's emitting lots of ultraviolet, and that's why you get such ionization of the gas around it. Question?
You just said that the star throws off.
Yeah, this is...
Or does is it solar wind, or is it the lack of gravity?
So this is a complicated subject. This particular object is not a single star, a main sequence star. This is a star that has gently, not blown, but sort of wafted off its outer layers and left behind its core. So it turned into a red giant. The outer layers were being held on very loosely by gravity because they were so far away from the center, and then it's easier for them to be pushed away from the center. But then you have weird things happening, like there's the interaction of this very strong stellar wind with the gas, and there's the ionization, which goes into it. In this case, there was probably a second star orbiting around the first star. You'll notice that there's some complicated kind of structure here. It's not just a cloud. It's a cloud with this, it looks like little rings and spirograph. I can see what they call it, the spirograph. And that's probably because there are two stars going around each other, which are imparting motions to the gas, and the gas collides with other gas in a very organized way because of the orbits. Planetary nebulae are a very complicated subject. You should talk to Joel Kastner, one of the professors here, and not to me about them, because I don't understand them. It's too hard for me. Yes? So when a star goes supernova, it blows the layers off energetically, and they go flying off at high speed, and they would not stick around. This gas is sticking around here. They would go woof, and it would look like this. Like this, like that. So it would go boom and blow the outer layers off in a very violent manner, creating something that we can look at this particular object, which was seen to explode in the year 1054. We can actually take pictures how many years apart?
27.
We can take pictures many years apart, and we can see the outer gas get bigger and bigger and bigger because it was thrown out so fast. It's still traveling at thousands of kilometers per second into space. That's the result of a supernova explosion, and that's the physical processes involved there are way different and way more complicated and harder to deal with. All right, well, it looks like people are tired, so I will stop here and we can all go home.
All right, I know Dave Bishop is always looking to go to Applebee's afterwards. Is that still the case tonight, Dave? Yeah. I unfortunately have to go home to my baby. Any further questions regarding anything? If not, we'll wrap things up here. Thanks, everyone. All right, great talk, Dr. Richmond.